So we'll start in our Robot Project Center. We can create this code inside our autonomous mode like we did and demonstrated in the previous webinar, or we can create a brand new VI. Let's do that now. So we're going to create a new VI targeted for the NXT. We're going to enter a name for this. Call it the State Machine Demo. And now we've got a blank VI. So where to start? Well, the two things to remember about a state machine is that they always are comprised of a while loop and a case structure. So let's begin there. From our NXT programming subpalette, structures palette, we'll place down our while loop. Inside the while loop, we'll pull up the next structure we need, which is the case structure. We'll place that here. And the next thing we need is a shift register. Remember, to create a shift register, we right-click on the edge of our while loop and say Add Shift Register. The purpose of the shift register in a state machine is to remember the current state. And we'll see how this is used and how we benefit from this piece of the structure very shortly. Remember also, when we use a shift register, we should always initialize it. So if our shift register is going to remember our state, what should be the initial value? Well, let's go back to our state diagram. We start here, and our initial state is to go into the idle state. So let's go back into LabVIEW, create a string constant, which can be found from NXT programming, string constant, place that outside our loop, and type in idle. This is the initialization value of our state, so we're going to wire it into the left side of the shift register. And now we've got our shift register automatically taking the form of a string data type, turning pink. And this is going to be wired into our case selector. We'll just align things a little bit to keep our code nice and clean. Wire that guy right into there. And notice that when the case structure has a string wired into it, that the information available in the case selector has now changed to strings. So now we've got true in quotation marks, meaning that it's a string. So let's actually start off, and instead of wiring in the true case, we're going to describe the idle case. And just by typing idle there and pressing enter or clicking outside it, we've changed that case now to be the case called idle. So inside our idle case, let's take another quick look and see what we're supposed to do. Well, there's only two ways to come out of the idle case. And we're going to focus on the first, which is object detected. Afterwards, a little bit later, we'll also code up the second transition, which is reading the touch sensor. So in order to read and determine if an object has been detected, we're going to go to our NXT.io, drop down a sensor block, to read our ultrasonic sensor. We need to wire up our port, and in this robot configuration we want port 2. And finally, in order to determine if an object is detected, as we've done in previous webinars, we need a comparison. We need to read this ultrasonic distance and see if it's close. So in order to do that, we bring up our NXT programming palette, comparison, and drop down a less than comparison. Wire up the top terminal to the output from the function, and a constant, in this case, of 10 to the bottom terminal. So now we want to do something different depending on whether an object is detected or not. So whenever we do that, we've got two choices. We can use the select function, as we saw in the previous webinar, or we can use another case structure. Well, let's use a case structure for now. So again, I'll bring up the structures palette, put down another case structure, wire up the comparison result to my case selector. And if an object is detected, what is the action that we want to take? Well, this is a good question. We know that if we have detected something, we want to make the robot start moving. But the way we program a state machine is to make sure that we actually transition to the right state and let the states do the action. So rather than creating a move command now, all I'm going to do in the idle case is change my state by doing a control drag on this constant to be forward. And this is where the beauty of using the shift register comes into play. By wiring this guy up into the right side of my shift register, I've now said that the next time through this loop, forward is going to come out of this side, and we're going to then transition into our other state. This right here is the heart of the state machine. The while loop, the case structure, and the shift register. So what happens if no object is detected? Well, in that case, we're in the false case. And really what we want to do is we want to do nothing. But in order to do nothing, we have to be a little bit explicit. We have to actually say we're going to stay in the idle case. So instead of wiring and putting another constant here, what I've done is actually wired the previous value all the way through. So if we're in the idle case, nothing is detected, we go back into the idle case, and the whole loop repeats. So next, let's finish the last piece of the idle case, which is to determine what happens and to program the response when a touch sensor is read. So this can happen actually outside. Well, this is actually an interesting question, is how to implement this. We could put the touch sensor read inside the idle case, but if you notice really carefully, all three of the cases, the idle, the forward, and the backward case, all respond to the touch sensor in exactly the same way. So we can actually save a little bit of programming time by leveraging that. And actually, instead of putting it inside the idle case, let's read our touch sensor by going to the NXT-IO palette, sensor block, pardon me, read touch pressed, which is the default behavior. Make sure we define our port, which for this robot configuration is port 4. And what we really want to do is, if this guy is pressed, we want to stop the loop. Well, we've got our loop condition. Oops. We've got our loop condition here. We can just move it up to make our code nice and clean and read it here. The last piece that we're going to do is we're going to take advantage, as is good programming practice, of the NXT terminal to properly sequence our code. So I'll just shrink this case structure down and use the NXT terminal, have it come right through the edge of my case structure, bring this guy up and align him to make sure that I'm reading my touch sensor after the code inside the state machine is executed. So what we've done now is actually completely code up what we need to for the idle case. We've actually got a little leg up on the forward and backward cases because we've already programmed these transitions in. So the next thing to do is to move on and program our forward case. So we've got our case structure. Right now we've got the false case, which is there by default, and we've got our idle case. So let's change the false case now to be called forward. And inside this case, let's perform the actions we need. Well, we need to start moving the robot. So as always, we go to our Tetrix palette, put down our move DC motors function. We're going to create a constant for our motors, define it to be left wheel, click our triangle to expand it, to then add right wheel. We've seen this trick in previous webinars that we know we're going to use this motor constant somewhere else, so we can drag it outside of our while loop so it can be used just by wiring it in. We rewire up into our move DC motors function. Now we just have to give it some speed values. So we're going to right click to create constants because we want to move forward. We're going to give them both the same speed, and in this case it doesn't really matter what the speed is, we'll just give it a value of 50. Okay. Return back to our state diagram, take a look. Okay, so we've got our move forward state, we've started the robot moving, and what we need to do now is after 1 second transition into the backward state. So in order to achieve that, it's really simple. Let's just create from our NXT programming palette, from our NXT-IO palette, a wait for function. Place this down, choose our delay to be 1 second, wire up our NXT terminals as we have always up till now, and we're just going to reposition this stuff slightly take advantage of the positioning of our NXT terminal that we've previously got, keep everything nice and clean and lined up so that it'll be easy to debug later on. We've got almost all the way there. What we haven't done yet is wire something in for the next state. Well, you notice, unlike the idle state, which has a decision to make whether to move forward or to stay in idle, forward really only goes on to backward. So we don't need to do a condition check here. All we have to do is create a constant on our string and call it backward. So we're almost completely done our state machine. The last piece of the puzzle, naturally, is to program our backward state. So this is where using the string-based approach and using the case structure can actually make things really simple. So we can take a shortcut here. I'm going to right-click on my forward case and choose to duplicate this case. What that does is it creates a brand new case. It's unnamed. All we have to do is give it a name. I'll now call it backward. And now we can tweak this code to do what we want. So instead of moving a value of positive 50, we want it to go the other direction, so we change the value to negative 50. The backward state, again, after 1 second will transition, but this time, instead of transitioning into the backward state as the forward did, backward state is going to transition into idle. So we just have to change this constant now to be idle. And the last piece we need is to actually stop the robot after moving backward for 1 second. So we can go again to our Tetrix palette, our Tetrix stop DC motors, drop this down, break our sequencing NXT wire here, and insert the break instead. Keep everything nice and lined up, and wire up our motors constant. So now we're almost completely done. If you take a look at the state diagram, well, we've kind of done everything. We started off by initializing into the idle state. Idle transitions into forward. Forward transitions into backward. Backward transition into idle. All three of the cases, all three of the states will transition into the stop state. The only thing we need to do is, one, a little bit of housekeeping. Notice that our VI is actually broken. And the reason that it's broken right now is, if we click it to see the list of errors, it's coming from the case structure. There's no case for some selector values. This is an important subtlety and something to understand when you use strings or numerics as inputs to your case structure selector. As opposed to a Boolean value, which only has two possible values, true and false, there actually are essentially an infinite possible number of strings that you could wire in here. And we've only defined what to do in 3 of them: forward, backward, and idle. So all we need to do to solve this problem is we need to tell LabVIEW which of these to run if something else comes in. This is called making a case default. And the best approach is to take your least, your state or your case which is least likely to cause a problem or to cause movement, right-click on it, so I've switched to the idle state, right-click on it and say, make this the default case. It puts in the title the word default in addition to idle, and notice that our VI isn't broken anymore. So we're almost completely done. One last little piece of housekeeping. We want to make sure that the motor stops after the button's been pressed. So let's take a copy of our break function, do a control drag to bring it outside of our loop, wire it up through the NXT terminal to make sure the sequencing is taken care of, and wire the constant in. And this will make sure that whenever we transition from any one of these states into the stop state, not only will the program terminate because the while loop stops, but we give a break command to the Tetrix DC motor controller and we stop the robot from moving. So in summary here, without a whole lot of time and a whole lot of effort, and in fact by reusing what is essentially just 2 structures and a shift register, we've programmed up this state diagram. The nice thing about this approach is you can imagine, let's expand this. Let's add 5, 6, 10, 15 states. Although the diagram gets more complicated and your logic might get more complicated, the structure of your code doesn't really get that much bigger. You add more cases here, but the overall size of your code and the ability to test it, look at it, and understand it still remains. And this is why the state machine's architecture is such a commonly used approach when professionals are using LabVIEW for robotics and even other applications. And the last thing to quickly discuss is a little sneak preview of next webinar, where we're going to expand the functionality of this state machine to include not only slightly more complicated behavior, but to make it more responsive. One of the things you'll experiment with when you run and program and test this program, that the behavior when the touch sensor is pressed will often take a second to happen. And that's really obvious from the way we've coded everything up. That we've got a 1 second delay here before it's going to even read the touch sensor in both the forward and the backward cases. We can make a more sophisticated approach to this state machine architecture, which will allow the system to be much more responsive. And that's what we're going to talk about in the next webinar. So on behalf of myself and Greg and our friends at National Instruments, thank you very much for watching this 6th in our webinar series of how to use LabVIEW for the FTC competition. Have a great afternoon, and we hope to see you next week.